It's a little bit weird, though, to multiply two vectors and end up with something that isn't a vector. So can we invent a method of multiplying two vectors that gets us a third vector result? The number line isn't the only way we learned how to multiply numbers. Suppose we wanted to multiply the numbers 3 and 4. Back in grade school, we might have learned a method that makes rows and columns. 3 rows of, or 3 rows of 4 dots each. And we count up all the dots. And the answer we get is 12. So that's the product. I mean, it's also the area of a rectangle, 3 units by 4 units, which is, I mean, this okay, yeah, that's this grid, 3 units this way and 4 units this way. Yeah, is okay. 3 by 4 is 12. Three and 4 oriented in right angles this way, sort of spread out through the two-dimensional space in the, oriented at right angles in a plane, describe an area. And they describe an area according to their product. For each of 3, 1, 2, 3, include 4. 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4. For every of 3, include 4, and vice versa. All right. Let me redraw this here. For every, just holding that thought in my head, for every of 3, for every of the first thing, include the second thing. All right. A is 1, 2, 3, 4, 5. B is 1, 2, 3, 4, 1, 2. So that's A. This is B. And now I'd like you to think for each point along vector A, do vector B. For every of 3, include 4. For every of A, include B. For every point along A, include an instance of vector B. Okay. That includes the end. From here, go 4 units to the right and 2 units up. And for each point between there and there, do the same thing. Go 4 units to the right and 2 units up. 4 units to the right and 2 units up. 4 units to the right and 2 units up. Everywhere along vector A until what you've ended up drawing is an area. It's not a rectangle, but it's still an area. It's the area of a parallelogram defined by, spanned by A and B. What is the area of this parallelogram? Because remember, in normal 3 by 4, the area is the product. So if we want to multiply A and B, the area spanned by them is their product in at least as far as this kind of multiplication goes. The area of a parallelogram, let me erase some of this cross-hatching here so I can draw. Area of a parallelogram is 1/2, no, I'm sorry. It's just base times height. Okay, so B is the base, I guess, and the height is here. If we knew the angle between A and B, the height is a sine phi times the base. Oh, cool. A sine phi times the base. What if we were curious about the other, what if we looked at it the other way? What if A is the base and B is the height? Same story. We find the height with vector B times the sine of phi multiplied by the base, and we end up with the same expression. A times B sine phi, same expression. Okay, cool. So we know how big it is. We know its size. We know the square footage of this area. How do we get the result to be a vector? The convention is to leverage what we know about right-handed coordinate systems. Vectors A and B make a plane. They define together a plane. It's the XY plane in this case, but it's the plane of the board. How can I specify what plane that is? Well, I can say that it's the XY plane, but I need to use 2 vectors to say that. It's the plane defined by the x-axis and the y-axis perpendicular to it, but that I need 2 labels for it. The z-axis is the direction perpendicular to this plane. And there's only one direction perpendicular to this plane. It's into and out of the board. Saying that it's this many units, A, B sine phi, it has an area that big in the z direction means that it's the z direction that is perpendicular to the area spanned. Now, okay, is it into or is it out of the board? And the answer is that according to the right-hand rule, we multiply B cross product A, vector B cross A, and we use the multiplication X, old time symbol there. Start pointing ourselves in vector B. Point your fingers in the direction of vector B. then cross them around into vector A without breaking your knuckles. Your thumb points in the direction of the result, out of the board. That's according to the right-hand rule. That's the only way you can do that. Otherwise, you're trying to take your hand like this and break your knuckles to get your hand to force the other way so that your thumb points into the board. It's not the way your hand goes, so it's not the way the answer goes. Start pointing in vector B, curl them around to A. If you can do that, your thumb points out of the board, and that's the direction of the answer. And the reason that's true is so that the X direction cross the Y direction equals the Z direction. I cross J equals K. That's how we define what it is to be a right-handed coordinate system. The X crossed into the Y, the Z-axis points out of the board at our face. Okay, so the answer has a magnitude this big, A, B sine B, and is in a direction, unit vector hat, that is perpendicular, because that's how we can specify a plane with one vector. Perpendicular to what? To both A and B, according to the right-hand rule, RHR. This symbol is my own invention. You're not going to find it in the textbook. It's clunky as hell, but it says everything we need to say. This magnitude in a direction perpendicular to both A and B, according to the right-hand rule. Note the way that we define the vector product, because this is a vector result. It's a magnitude and a direction. The way we define the vector product means that it is not commutative. A crossed into B, and it's helpful if you say into. We call this the cross product because we're using the multiplication cross instead of the dot for the dot product. A crossed into B, we start with our fingers pointing in A, curl them so they point in B, and our thumb points into the board, opposite the answer we got a second ago. The cross product, the vector product, is anti-commutative. We switch the order, we introduce a minus sign. Okay, cool. This is true. I'm going to make this a definition. We can always come back to this. This is always true. We would like to have a component-wise way to complete the vector product, just like we had a component-wise and a magnitude version for the dot product. We had an AB cosine, and we had the version that was AX BX plus AY BY plus. So we'd like to have a version for the vector product that uses only the components, AX, BX, AY, BY, whatever that turns out to be. This definition and the fact that we want it to go in the cycle from I to J to K is enough to get us to an answer. All right. For completeness, we got to finish what is J cross K. Okay, Start with your fingers in the direction of the J, the y-axis. Curl them so that they point in the direction of the z-axis and your thumb points in the x direction. What about K cross I? Okay, hold on. Let me get my hand to do this. Start with your fingers in the Z direction, out of the board, back at your face. Curl them around so they point in the X direction without breaking your knuckles. Your thumb points in the Y axis, as we've labeled it. Think about old school video games like Pac-Man or something, where when you run off the right side of the board, you show up on the left side and you can circle around the world that way. This is kind of the same way. Think about I, J, and K in that order on the board. If we run to the right from K, we loop around back to I. If we start from J and go forward to K, if we keep going, we're going to loop around to I. Start with J, then K, then I. We start with K, then I, then J, always in that order. If we multiply them the other way, we introduce a minus sign. Okay, you ready? Suppose that we have, for clarity, so that it's less confusing. Believe it or not, this will be less confusing. A sub x, a sub y, a sub z in the k, b sub x, b sub y, b sub z. Suppose we have two arbitrary three-dimensional vectors, and we want to cross product them together. We want to find the vector product of A cross into B. We do what it says. AX, AY, oops, see, I'm so used to two dimensions, plus AZK cross. And I gotta erase this, but you remember. X plus BY plus BZ. And I gotta erase this, but again, you remember. Get back to it. Okay, so we gotta do what it says, and we need to distribute. We need to FOIL trinomials, so we're gonna end up with 9 terms. It's worth doing once, so I'm gonna do it with you, and then we don't need to do it ever again. AXI, BXI with a cross. AX, BY. Oh, shoot. AX. All over the place today. AXI cross BYJ plus AXI cross BZK plus AYJ cross BXI. And now we can kind of follow a pattern. Now on each row, we'll use AY, and on each column, we'll keep BX, 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 BY, BY, BY. AYJ cross BYJ plus AYJ BK plus, next line, A Z K cross B X I plus A Z K cross B Y J plus A Z K cross B Z K. All right. One thing we didn't talk about, what happens if we are finding the dot product of two pieces that are in the, or I'm sorry, the cross product of two pieces that are in the same direction? A, B, sine, phi. The magnitude of the first piece is AX. The magnitude of the second piece is BX. The sine of the angle between the X direction and the X direction, the angle there is 0. The sine of 0 is 0, 0. If we are asking for the cross product of two pieces that are not perpendicular because they are parallel, the answer is 0. This is better. 3 of the 9 terms just canceled immediately. All right, cool. And we can simplify things a little bit. We know that I cross J is going to be K. So this is AX, BY, K. J cross I is the backwards. That's the, we've done, it's commutative. So it's the magnitude of the first piece, the magnitude of the second piece, times, that gets us negative K direction. So we could combine these two terms if we put the minus sign out front. And we could do a similar trick. Here we're going to get, let me keep different colors. It might help things line up nicely. Here we get AX, B, Z. Now I cross K is the backwards of K cross I, which we said was J. So this gets us a negative J. I cross, wait, K cross I, that's forwards, that's going to get us a positive J. We could write this with a positive J if we pull the minus sign out front. J cross K gets us I. K cross J gets us negative I. If we pull the negative out front, we really only have 3 terms. Once we combine like terms, we've got an I hat term, a J hat term, and a K hat term. This is great. That's a vector. I'm completely out of space to write it. I guess I'll put it here. A cross B equals, take the i's first, this one minus this one, so A Y B Z minus A Z B Y in the I direction. And you can start to see kind of a pattern developing. The X direction of the cross product only involves Y and Z components. It doesn't involve any X components. And we start with X, we start with the next letter, and then we use Z, and then we switch them. A Z BX minus AX BZ. Again, we're talking about J. The expression doesn't use any Y components. We're starting with Y, we look at the next letter AZ, okay, BX, and then we switch them. AX BY minus AY BX. And again, the Z component uses no Z components of the factors. We starting with K, we loop around to I, that's next. So AX, then BY, and then we switch. So this is our kind of unwieldy formula for the component-wise vector product. We do end up with a vector. It explicitly has 3 components. This is not the same as the dot product, the scalar product. When we were done with that, we had no more hats. The dot product got rid of them because it only wants to talk about things that are parallel and how parallel they are, and just add up those, contributions. Here, vectors A and B define a plane, and we need to talk about the vector that is perpendicular to that plane. So we need components in order to do that. If you look up the vector cross product, you might see it written like a matrix determinant. That's fine. It's a perfectly nice way to write it, I suppose, if you like matrices. The only hiccup there is that it's often written with the J component backwards. So you might sometimes see the cross product formula written with a minus sign introduced for the you might see it written this way, blah, 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 minus, switch the order. AX, BZ minus AZ, BX. And the reason to do that, we can argue about whether it's a good or bad idea, but the reason to do that is so that if you have a matrix determinant and you're talking about the J, AXBZ, we formed a little submatrix to calculate the matrix determinant, and the main diagonal is AXBZ, which is the -1 in our actual formula. So they put the minus sign here when they write it with a matrix determinant so that AXBZ comes first. It's just a different way to write this thing that we wrote in black ink. The matrix determinant way to write it is cute, but not especially helpful, I don't think. Especially when this expression, these components, are listed as formulas at the end of chapter 1. So we can always go back and just get the component expressions straight up, never mind a matrix. It's always there for us. On Wednesday and Thursday, we will look at some We'll do some worksheets that allow us to practice these things, and yeah, that's vector algebra. There's one kind of real quick there okay. Let me record one more quick segment.